So this whiteboard is visible to everyone.
Yes, sir.
Okay, so you can download the actual tutorial sheet from the MS team. Some setting get disrupt when we copy it in the whiteboard. So particularly the superscript and subscripts are not visible uh, clearly in the whiteboard. So please download the actual tutorial sheet from the MS team and then start solving. Okay, so what is been given here is let's look at the first problem. So in the first problem, what is given is an oil flowing through 25 mm diameter pipe exchanges heat with an external medium. At a particular section of the pipe, the radial velocity and the temperature distribution in the oil are given. So V is given at 0.5 800 R square and T temperature distribution is given as T equals to 60 plus 1.728 into 10 raised to the power 5 R square minus 3.072 into 10 raised to the power 6 R cube, where V is in meter per second, R is in meter, and temperature T is given in degrees Celsius. So determine whether the oil is in laminar or in turbulent flow. Is the oil being heated or cooled? Calculate the average velocity of the oil. Calculate the cup mixing temperature of the oil at the given section. I will explain you what is this cup mixing temperature is. And then find the local wall heat flux, heat transfer coefficient and Nusselt number. Okay, so what has been given is there is a pipe. The diameter of the pipe is given. So diameter of the pipe is given, that is 25 mm. So that means radius is given as maybe I'll just so R naught radius is given as 25 by 2, so that becomes 12.5 mm. So 12.5 into 10 raised to power minus 3 meter. Okay, this is what is been given. Further, what is been given is velocity distribution is given. Velocity distribution given as 0.5 minus 800 R square, and similarly the temperature distribution is given as 60 plus 1.728 into 10 raised to the power 5 R square minus 3.072 into 10 raised to power 6 R cube. So this is what is been given in the problem statement, isn't it? Correct? Let me just, I have not started my videos. Okay. Okay. So now we can rearrange this velocity profile. See, in the velocity profile, V is given at 0.5 minus 800 R square. So clearly the velocity is a function of R square, isn't it? So if you remember your fluid mechanics, probably whatever you are doing right now. So in a laminar flow, velocity is related to R square, whereas in turbulent flow, the velocity is related to R raised to the power 1/7, isn't it? Something like that. So clearly here in this case V is related to R square and therefore it should be laminar, but we will rearrange this equation little bit more so that it will be clear to you why we are saying that the flow is laminar. Okay, so velocity is given here as 0.5 minus 800 R square. So from this we can rearrange 0.5 I can take out. So 1 minus 800 by 0.5 R square. So this becomes 0.5 into 1 minus 1600 R square, isn't it? Now, what is the radius here? What is the radius? The radius here is R naught is given as 0.0125 meter. So if we put it here in this particular equation, let us see what we get. So if we put it here in this equation, V 0.5 1 minus R divided by 0.0012, sorry, 125 this entire thing square. So this is exactly same as what we have represented here, isn't it? 1 minus 1600 R square. This is exactly the same, isn't it? If I square the 0.0125 and take its inverse, it comes out to be 1600. So it's perfectly matching with whatever the equation we are having. And this equation is what? This equation, therefore, we can write down this equation as 0.5 1 minus R by R naught whole square, something like this, isn't it? So this is the equation for the laminar flow. This is the equation for laminar flow, isn't it? Correct. So for laminar flow, V is given as V max in the bracket 1 minus R by R naught whole square. This is what the equation for the laminar flow is, isn't it? So therefore we can conclude here is, what we can conclude here is the flow is laminar. Therefore flow is laminar. Flow is laminar with maximum velocity, max velocity V max equals to 0.5 meter per second. Okay. Is it clear to everyone? Hello.
Hello.
Yes.
Sir, a factor of 4 should also come.
Factor of 4 should also come where?
1 divided by 0.125 whole square is 6400.
Just let me check. Let me check, just wait. Just wait. I think I made a mistake, not here. In some other thing we have made the mistake. Okay, just wait. 25. Okay, I got it. Yes, you are absolutely correct. The mistake what we have done here is in the problem formulation itself. Okay, let me just correct that in the tutorial also. Some change here and there we are doing. This is actually creating the problem. Let me just correct it. Let me just correct the problem statement itself. Okay. You are absolutely correct. The correct statement is this. Correct statement is this. This is 25 mm radius is there. It's not diameter. Some change are happening here and there because this file is taken from last year. So let me just correct it. Okay. Just quickly correct it. So please correct the statement. This is 25 mm radius. I will update the tutorial sheet in there, but you make the correction here. Okay. So this is then perfectly matching with whatever the equation we are having. Okay. Okay, now it is okay. Hello.
Yes, sir.
Is it perfectly all right? Okay, so let me just update it. Let me just update the tutorial. Give me just 1 minute. Okay, I'll just correct it here itself. Otherwise, the same file will move around. Delete. Okay, so I have updated the correct file now in the MS Team. Sorry for this typo mistake here and there. Let me just open the whiteboard. Okay, okay. So we can conclude here that the flow is laminar with maximum velocity Vmax equals to 0.5 meter per second. Okay, now next part is we have to calculate the wall temperature gradient. That is what is been asked in the second part. So second part is we have to calculate in part B, is the oil being heated or cooled. So that we can directly find out from this equation. T is given as 60 plus 1.728 10 raised to the power 5 r square minus 3.072 into 10 raised to the power 6 r cube. This can be done two ways. Either we can find out dt by dr, and if dt by dr is positive, that means as r is increasing, temperature is increasing, and that means what? The oil is being heated. That is one way of doing it. Another way of doing it is either put r equals to 0 and then r equals to 25 mm, isn't it? So that is 0.025 and compare both the values. You will get the answer. Okay, so can you do it? Is it clear to everyone?
Yes.
Yes, sir.
Okay, so what is been given is there are two ways we can find out whether the oil is being heated or not. So T is given. So T is given as 60 plus 1.728 into 10 raised to power 5 r square minus 3.072 into 10 raised to power 6 r cube. So at t at r equals to 0, what we are going to get is 60, isn't it? Similarly, we can find out t at r equals to 0.025. So that comes out to be 60 plus 1.728 into 10 raised to power 5 into 0.025 square minus 3.072 into 10 raised to power 6 into 0.025 cube. What is the value? Anybody? This is in degree Celsius. So this comes out to be 60 plus 1.728 into e raised to power 5 into 0.025 square minus 3.072 into e raised to power 6 into 0.025 cube. Is it 120? Hello? Is it 120?
Yes, sir.
So that means the temperature at the wall is higher than the temperature at the center of the pipe. So what it means, when we can have such situation, we can have such situation only when the oil is being heated from outside, from the uh, uh, the uh, wall of the pipe, isn't it? So that means the oil is being heated. So this gives the information that oil is being heated. We can find out the same thing again by doing another way. So we can differentiate this dt by dr, we can find out, and we can find out dt by dr at r equals to r naught, and if that comes out to be positive, it clearly means that the oil is being heated as we are moving along the r, isn't it? So both ways we can prove that the oil is being heated. Now the third part is we have to find out the average velocity, isn't it? So our average velocity is obtained as, in part C, what is being asked is the average velocity is being asked, isn't it? Calculate the average velocity of the oil. So average velocity is given as, average velocity is given as Vmax by 2, isn't it? So Vmax we already know 0.5 by 2. So that comes around 0.25 meter per second, isn't it? Part D is we have to find out the cup mixing temperature. Cup mixing temperature. Now what is cup mixing temperature? Cup mixing temperature is nothing but the bulk temperature. Generally, how bulk temperature is calculated? It is average based on the energy. Okay. So the formula used for the cup mixing temperature is this. This formula we will be regularly using. So 0 to R naught, 0 to R naught, rho Cp 2 pi R V dr into T. Okay. And in the denominator, what we are going to have is R to R naught rho Cp 2 pi R V dr. Okay. This is the equation. So can you solve this integral and find out what is the cup mixing temperature in this case? So TCM 0 to R naught in this case is R naught in this case is 0.025 R 1 minus 1600 R square. This is the velocity. Rho Cp pi 2 pi, this we can consider constant. So this will get cancelled out because this will come out from the integral sign. And here again multiplied by 60 plus 1.728 into 10 raised to the power 5 r square minus 3.72 into 10 raised to power 6 3.72 3.072, isn't it? 3.072.
So there was the factor of 0.5 also
Where?
for V.
Just wait. R cube dr. Okay, where you are saying?
Okay, it would get cancelled out. Okay.
Sir, can you tell how this formula has been derived?
Yes, I can give you the physical significance of this. Just wait. Let me just write down 0.025 rho Cp. So that get cancelled out. So rho Cp we don't require. R into 1 minus 1600 R square dr. Okay. So what this formula is, basically this calculates the average, temperature across the pipe by considering the variation not only in terms of temperature but also in terms of the velocity. So if you look at the numerator here, both the variation in the velocity as well as temperature is considered. Remember here V and T both are the function of R, isn't it? And that is divided by only the variation in the velocity. So it is in a way the averaged over energy. It is in a way the cup mixing temperature is nothing but the averaged over energy across the cross section of the pipe. Okay. So this is the typical formula. This is the standard formula used for calculating the cup mixing temperature, where not only the distribution of velocity but also the temperature is used in the numerator and divided by the only distribution in terms of velocity. Okay, clear? Is it clear? This is averaged over energy. Is it clear to the student who
Yes,
asked?
sir.
Okay. So can anybody calculate this integral? I have not calculated this integral. Please calculate and tell me the value. Anybody? Can anybody calculate the value of this and calculate the value and give me? I have roughly calculated the value. Just check whether this value is correct or not. I am not sure whether this value is correct or not. But this should come around 85.028 degrees Celsius. Just check whether you all are getting the same answer or some other answer. So in some calculator you can calculate the integral directly. Please use that and let us know whether this value is correct. Anybody got the value?
Sir, it is coming 85.027.
So this value which I have written is correct?
Yes, sir.
Okay. So now let us move to the next part. In the next part, what we have to find out is find the local wall heat flux. Find the local wall heat flux. So what we have to find out is local wall heat flux So basically what we are interested is K dt by dr at r equals to 0.025. Remember, it is wall hit flux, so we wanted to find out at r equals to 0.025. Okay, so find out this variation in the temperature is already given, so you can differentiate that. You can differentiate that. So what you are going to get is this will be equals to K into differentiation of the temperature is going to be 1.728 into 10 raised to the power 5 into 2 R minus 3.072 into 10 raised to the power 6 into 3 R square, and this has to be found out at R equals to 0.025. Okay, so put the values here. K is also given. K is given as 0.138, isn't it? If I'm not wrong somewhere, the K is given as, yes, 0.138. Okay, so put the values here and find out what is the local wall heat flux. So what is the value? Anybody? 728 into e raised to power 5 into 2 into 0.025 minus 3.072 into e raised to power 6 into 3 into 0.025 square. So what we are getting is this will be 0.138 into 2.88 into 10 raised to power 3, and that should be equals to multiplied by 0.138. So this should be equals to 397.44. Is it correct?
Yes, sir.
Okay, so now based on this, let me just correct it. 0.025. Okay, so what we are getting here is the local wall heat transfer coefficient, and now based local wall heat flux we have got. So now we have to calculate the heat transfer coefficient, so that we can directly obtain as so heat transfer coefficient is given as heat transfer coefficient in this case will be what? Heat flux by driving force. So that is nothing but K dt by dr at r equals to r naught divided by Tw minus T naught. Tw minus T naught. Okay. So that will be basically H. Isn't it? Is it correct? Remember the heat, what will be the total heat transfer obtained here? The heat flux, heat transfer obtained here by convection will be H A delta T, whereas the heat transferred by conduction in this case is going to be A K dt by dr at r equals to r naught, isn't it? So that A get cancelled out. So ultimately heat transfer coefficient H is obtained as K dt by dr r equals to r at r equals to r naught divided by Tw minus T naught. isn't it? Again, one more thing to note down, which is very important here. See here, the flow is laminar, and that is why we have used this temperature as T naught. T naught here, remember, T naught is the temperature at the center. Temperature at the center is 60 degrees Celsius. So that is why we are using the temperature at the center as 60 degrees Celsius. But if this flow would have been turbulent, then which temperature we should have used? We should have used TW minus T cup mixing temperature or T bulk, that we should have used in case of turbulent flow. But here we are looking at the laminar flow. That means the resistance is from the wall to the center. This entire layer from the center to the wall, this act as a resistance in case of laminar. In case of turbulent, only a small thin layer which is very close to the wall, that act as a resistance. So that is the difference. This TW we are using only because it's a laminar flow. If it would have been turbulent flow, we would have used T cup mixing or T bulk. Both are same. Okay, so in this case, we know all the values. We have calculated all the values so far. So this becomes 397.44 divided by TW. We have already calculated, that is 120 in minus 60. So calculate this H. So what is the value of H? Anybody? So 6.624. 624 watt per meter square degree Celsius. So this is the unit. Okay. What is the last part? Last part is we have to find out the Nusselt number, isn't it? So Nusselt number, I'll just quickly do it. Nusselt number in this case, this is 6.624. 6.624. So this becomes 6.624. 624. Okay. So what is the Nusselt number? Nusselt number is HD by K. Everything you know, isn't it? So Nusselt number in this case is HD by K, isn't it? So H is given as, in this case, 6.624 into D is 2 into 0.025 by K. K is 0.138. 138. So what is the value? Anybody?
2.4.
So this comes around 2.4. Let me just write down. 2.4 is the Nusselt number. Okay. So let me just correct it in my. This is 6.624 into 0.025 into 2 divided by 138. So this becomes 2.4. Okay. Perfectly all right. Okay. So can we move to the next part?
Yes, sir.
Okay. Now let's look at the second question. Second question is again slightly more time consuming. So I hope that you are having some more time. Do we have any class after this? Can we extend for 10 minutes? 5-10 minutes? I will just copy it as it is. Let me just copy the problem statement. Okay. Now in this particular problem, what is been given is mercury is purified by distillation, is cooled by passing it through a double pipe heat exchanger. So there is a double pipe heat exchanger. If you look at the system is something like this. I'll just quickly draw. So there is one inner pipe, isn't it, through which the mercury is flowing, and then there is a outer pipe. Then there is a outer pipe from which the water is flowing. Okay. Okay. So here is mercury, and here is the water. What is the temperature? Inlet temperature of the mercury is 250 degrees Celsius. So here the temperature is 250 degrees Celsius. Outlet temperature here is 40 degrees Celsius. The water temperature is enters at. So here the water temperature is 26 degrees Celsius and the outlet temperature is 40 degrees Celsius. 40 degrees Celsius. The properties are given. Now what we have to find out is the length of the tube required. Okay. So I will again go through the statement. Mercury purified by a distillation is cooled by passing it through a double pipe heat exchanger. The inner tube internal diameter is 13.5 mm. So this is, I will just show by a different color. So this is 13.5 mm. This thickness is given as 2.75 mm wall thickness, and the outer diameter is the inner tube. Just wait. Outer diameter is this particular diameter is 41 mm. Okay, correct. So this is what is been given. Again, the mercury is flowing at inlet mercury is 1500 kg per hour. Okay, this is what is been given. Now we have to calculate what length, this particular length, this L we have to calculate. Okay, correct. So now first here we have to see, since mercury is flowing inside the inner pipe and the water is flowing from the annular region, first we have to see whether the flow is laminar or a turbulent, because based on that only we have to use the correlations required, isn't it? So let us find out the Reynolds number for the flow through the inner pipe, and also the Reynolds number for the flow through the outer pipe. So again, for the Reynolds number, what we require is dV rho by mu, isn't it? So mu is already given. Diameter of both annular as well as the inner pipe is also known, isn't it? But velocity is not known. But mass flow rate is given, isn't it? So mass flow rate is given. So from that we can find out the velocity, rho velocity into density, that particular quantity we can find out here. Okay, so let us first find out the area. For the flow, isn't it? So let me just scroll up a little bit. Okay, so area for inner tube. So for inner tube, the area A1 is given as pi by 4 d square. So inner tube, the diameter is 13.5, so that becomes 0.0135 square. So this area becomes 135 square. So this area becomes 1.43 into 10 raised to power minus 4 meter square. So this is the cross sectional area for the flow through the inner pipe. Okay, and for annular region, remember the water is flowing through the annular region. So for annular region, the area A2 will be given by, again, pi by 4. So the diameter here is the inside diameter of the outer tube comes is 41 mm. So that becomes 0.041 square, isn't it? But what will be the diameter here? What will be the diameter of the inside pipe? So that will be basically this 13.5 plus 2.75 on the this side as well as 2.75 on the other side. So that becomes 0.019 square. Is it clear to everyone? How come this 0.019 is coming? Because 13.5 mm is there, 13.5 mm plus 2.75 here at the top and 2.75 at the bottom. So that means 2.75 plus 2.75 becomes 5.5. So if we add 5.5 mm in this 13.5, that becomes 19 mm. So that is why we have used here 0.019 square, isn't it? So this comes out to be 1.037 into 10 raised to power minus 3 meter square. So this is the area for the annular region. Okay. Now mass flow rate we can calculate. The mass flow rate of the mercury. Mass flow rate of mercury. G1 is 1500 is given. So that is per hour is given. So that becomes per second. And if we divide it by, again, area, if we divide it by area of the flow, cross sectional area for the flow, so that is 1.43 into 10 raised to power minus 4. What we get is 2914 in the unit of kg per meter square second, isn't it? So this is same as rho into V, isn't it? This is same as rho into V. So Reynolds number RE1, Reynolds number for the first case will be given as dg1 divided by mu1. So that becomes d, we already know, 0.0135 into g, we have already calculated 2914 divided by mu which is given in the problem, isn't it? So in the problem, mercury, for the mercury, what is been given is density and the kinematic viscosity is given, isn't it? For density is given 13200 kg per meter cube and kinematic viscosity is given. Kinematic viscosity is what? Viscosity divided by density. So in this case, if you wanted to have viscosity, what we have to do? This kinematic viscosity we have to multiply it by rho, isn't it? So that is what is been done here. So mu1 is, in this case, is going to be 8.5 into 10 raised to power minus 8 into 13200. So this comes out to be 350. Okay. So this comes out to be 35,060. Now let us find out the Reynolds number for the, this is for the flow through the inner pipe. Now we have to find out the Reynolds number for the flow through the annular region, isn't it? So for that, we don't know what is the value of mass flow rate of the water coming out. We know the temperatures, but we don't know what is the mass flow rate. So we can make a energy balance, isn't it? I can go back and again explain. See, here the mass flow rate is known to us. So that is why we have calculated the Reynolds number easily, because this mass flow rate we have divided by the area and we have converted into a in the unit of kg per meter square per second, isn't it? So that is kind of the rho into V into rho. That is basically V into rho. Correct. But and therefore dV rho by mu we have easily calculated. But let us look at the water. For water, the inlet temperature we know, outlet temperature we know, but what is the mass flow rate of the water coming out or entering here, that we don't know. So we can calculate the mass flow rate by making a heat balance. So what will be heat balance? Whatever the heat lost by the mercury should be same as whatever the heat gained by the water, isn't it? So mcp dt for the mercury should be same as mcp dt for the water, isn't it? So that we can write down, and from that we can find out the mass flow rate directly. Okay. So heat balance. So heat balance in this case, we can directly write down heat balance Q. In this case, the mercury mass flow rate is given into Cp, which is 0.14 into what is the temperature change? 242, sorry, 250 to 240. Just a minute. So this becomes 250 to 40 degrees Celsius. So this is nothing but the heat lost by the mercury as it moves from one end to the another end. And similarly, we have to calculate what will be the heat gained by the water should be the same, isn't it? So let's the mass flow rate of the water is, let's say, mw into specific heat of the water is given as 4.2, and the temperature change is given as 26. So we can calculate the mw here by back calculation. So this comes out to be 750 kg per hour. Remember, this is given in kg per hour. So therefore mw will also have a unit of 750 kg per hour. Is it clear to everyone? So this we can convert it in a mass flow rate. So mass flow rate is given as this 750 divided by 3600 and divided by the area of the annular region. So area of the annular region we have already calculated, that is 0.001037. If you go back and see, that is what the area we have obtained for the annular region, isn't it? So this is 1.037 into 10 raised to power minus 3. This is what the annular region area we have obtained. So that I have divided here. So by dividing, what we get is, so this is nothing but G2. G2 is obtained as 201 kg per meter square second. Okay. Now we have to calculate the Reynolds number for the flow through the annular region. So that is Reynolds number 2. That will be dV rho by mu. So that is also given as dG2 by mu. But what this diameter is going to be, because here we are looking at the annular region. So for annular region, the diameter should be the equivalent diameter. So let's calculate the equivalent diameter of the annular region. So dE in this case is going to be what? 4 into area. Equivalent diameter is calculated like this: 4 into area by weighted perimeter. So this is the formula for the equivalent diameter. So 4 into area, we already know the area. So that is 1.037 into 10 raised to power minus 3 divided by weighted perimeter. In this case is going to be pi d, pi into the diameter in this case is going to be outer diameter, isn't it? So that is going to be 0.019. So this comes out to be 0.0695 meter. So that is the equivalent diameter. Now based on this equivalent diameter, we have to calculate the Reynolds number 2, RE2, that comes out to be 0.0695 into G2 is 201 divided by the viscosity of the water. Viscosity of the water we know, that is already given in the problem statement. So that is 7.3 into 10 raised to power minus 4. So this comes out to be 19136. Okay. Is it clear to everyone? Hello? Hello?
Yes.
So now by looking at both the Reynolds number, what we can conclude is both flow through the inner pipe as well as flow through the annular region, both are in a turbulent region, isn't it? Because the Reynolds number is greater than 10,000 in both the cases, isn't it? So now we can use the corresponding correlations and find out the overall heat transfer coefficient, and based on the overall heat transfer coefficient, then again we can make the heat balance and find out the length of the pipe required for a given heat transfer, isn't it? So now for the inner pipe, so what was flowing through the inner pipe? From the inner pipe, the mercury was flowing, isn't it? So mercury is nothing but what? Is it a liquid metal? Isn't it liquid metal? So for liquid metal, what is the correlation? If you remember the last class, in the last class, for the liquid metal, the correlation is given by Cedar and Tate. So what was the correlation? The Nusselt number was given as 5 plus 0.025 into Peclet number raised to the power 0.8. This was the correlation given, isn't it? Correct. So we can now Peclet number is what? Peclet number is Reynolds number into Prandtl number. Reynolds number we already know. Prandtl number we don't know. So Prandtl number is Cp mu by K. Cp mu by K, isn't it? So specific heat of the mercury is given as so 14.14 kilojoule per kg is given, so that becomes 140 into mu. Mu of the mercury is not there, so that we can calculate directly as 200 into kinematic viscosity, so that is 8.5 into 10 raised to power minus 8 and divided by K. So K for the mercury is given as 11.5. Correct. So what we get from this is 0.0149. That is what the Prandtl number we are expected to get. Now we can put it in the equation. So in the equation, Nusselt number is given as 5 plus 0.025 into Reynolds number we have already calculated, that is 35060 into 0.0149 raised to the power 0.8. So this comes out to be 42.3, and this Nusselt number is given as HD by K. So we can find out H as 42.3 into K. K in this case is going to be 11.5 divided by D. So that is 0.0135. So this comes out to be 36030 watt per meter square degree Celsius. So this is going to be the heat transfer coefficient inside the pipe where the mercury is flowing. So this is HI. Okay. Now similarly we can find out what will be the heat transfer coefficient for the flow through the annular region, isn't it? So for the annular region, what is been given is In the annular region, water is flowing. Water is a normal fluid and the flow is turbulent because the Reynolds number is much above the 10,000. So for a turbulent flow, what is the correlations? So for a turbulent flow, the correlation is Ditters-Boelter equation, isn't it? So Ditters-Boelter equation. So this correlation can be given as 0.023 into Reynolds number raised to the power 0.8 and Prandtl number raised to the power 0.4. Why 0.4? Because here, why 0.4? Because the water is being heated here. If it would have been cooling, in that case, we would have used 0.3, isn't it? So we can just put all the values here, 0.023 into Reynolds number we have already calculated, that is 19136 0.8 into Prandtl number. Prandtl number for the water is already given, isn't it? Prandtl number for the water is given, that is 4.9. So 4.9 raised to the power 0.4. So this comes out to be 115.7, and this is given as H naught D naught divided by K, isn't it? So from this, H naught can be calculated as 115.7 into K water. For the water, the thermal conductivity of the water is 0.615 divided by the diameter. In this case is going to be the equivalent diameter, that is what we have used in the calculation. So that becomes 0.0695. So this comes out to be 1024 watt per meter square degree Celsius. So this is okay. So now we have obtained the heat transfer coefficient for the inside pipe. We have obtained the heat transfer coefficient for the flow through the annular region. Now we can calculate the overall heat transfer coefficient. So overall heat transfer coefficient can be given as overall heat transfer coefficient. So overall heat transfer coefficient in terms of the inner surface area, that can be given as 1 by Hi plus Di by D naught H naught. So this becomes 1 upon 36030 plus Di is 0.0135. Outer diameter, again we have outer diameter considered in terms of the equivalent diameter, isn't it? So that becomes 0.0695 into H naught is 1024. So this comes out to be UI comes out to be 4600 watt per meter square degree Celsius. Okay, now only the last step is required. What we are interested in? We are interested in finding out the length of the pipe required for the heat transfer. So here the first type of balance which we have seen is the heat lost by the hot fluid should be same as the heat lost by the heat gained by the cold fluid. But what will be the heat transfer? Remember where this length will come. Length always comes when we are looking at the heat transfer. So the heat transfer is given as U A delta T LMTD, isn't it? Why delta T LMTD? If I go back, remember in the last class itself, I told that since the temperature difference is changing across the length, so here you can see the temperature difference is what? 250 minus 40. But at this end, what is the temperature difference? 40 minus 26. So this temperature difference is changing as we are moving from the right hand side to left hand side. This is not constant. When there is a temperature difference between the cold and the hot fluid is changing, in that case the delta T which one has to use, that is the log mean temperature difference, isn't it? So that is why Q is given as HA delta T LMTD. And what will be the area here? Area will be the area which is there at the periphery of this pipe. So that is going to be pi dl, isn't it? That is going to be pi dl. And from there we can find out L. In earlier balance, what we have done is we have only looked at how much heat lost by the hot fluid, that we have equated to the amount of heat gained by the cold fluid, isn't it? But there we have not said anything about the heat transfer. There we have not said anything about the heat transfer. We only said that this much amount of heat is lost by the hot fluid and this should be same as the heat gained by the cold fluid, isn't it? But how much heat transfer will be there based on the resistances, considering the resistances into the picture, that we have not at all looked at. And in the last step, that is particular thing which we are looking at. So therefore what we have done is we have first calculated the heat transfer coefficient for the flow through the inner pipe. So that is why we have calculated HI. Again, we have calculated what will be the heat transfer coefficient for the flow through the annular region here. So that is H naught. And then we have calculated what will be the overall heat transfer coefficient based on the inside surface area. So that becomes UI, capital UI. And now this total heat lost or whatever the heat gained by the cold fluid, that should be same as heat transfer, isn't it? The amount of heat is transferred between these two fluids. So that can be obtained as UA delta T LMTD, isn't it? Here area is going to be pi dl. And there we know pi, we know d, we know delta T LMTD. We can calculate the length of the pipe required for this particular heat transfer, isn't it? So that is what we are going to do in the last step. So this is Q is given as UA delta T LMTD. Q we already know. Q we already know. Delta T LMTD we can calculate. So delta T1 is going to be what? 250 minus 40. Similarly, delta T2 is going to be what? 40 minus 26, isn't it? And delta T LMTD is going to be what? Delta T LMTD is going to be what? Delta T1 minus delta T2 divided by ln delta T1 by delta T2. Okay, so that comes out to be delta T LMTD. This is 210. This is going to be 14. So this becomes 210 minus 14 divided by ln 210 by 14. So this comes around 72.4 degrees Celsius. That's it. So area here, area is calculated as Q divided by U delta T LMTD. U you have already calculated. So this is AI, isn't it? Because this is UI. So this becomes Q we already know. So total amount of heat transfer we have anyway calculated earlier, so that I can go back here. The total amount of heat transfer required, that we already calculated. This is the total amount of heat transfer, isn't it? So this is how much is the value? 1,500 into 0.14 into 250 minus 40, that becomes 4,100. But this will be per hour. Remember 1500 is per hour, isn't it? So that we have to convert in per second, isn't it? So that we have to first convert it in so CP is given as CP is, let's look at the unit of CP. Per kg is there, so that kg will get cancelled out. and this will be kilojoule per hour. Kilojoule per hour. Okay. Okay, this will be kilojoule per hour. Okay. So now let us look at the last part. So now put it in the original equation. So original equation is this. Okay. So now here area we can calculate, back calculate. So just wait. So here AI will be given as 44100 divided by UI is given as, so UI is given as 4600 into 72.4, that is delta T LMTD, isn't it? And 1 minute, some unit change, CP is 0.14. Let me just go back. Okay, so this is 1500 kg per hour into kilojoule per kg, 0.14 we have multiplied, and 4.2 kilojoule per kg, so that will be kilojoule per hour. So what we have to multiply is 1000. Okay, so what we have to do here is multiplied by 1000, so that is joule, into divided by 3600, so that is going to give me area. Okay, so 44100 into 1000 divided by 4600 into 72.4 into 3600. So this comes around 0.036, 0.0367 meter square. Okay, now this can be equated to, this is AI. So AI is given as pi dl, isn't it? So L in this case is going to be AI by pi d. So AI is 0.0367 divided by 3.14 into di. So di is 0. So this is going to be di 0.0135. So this comes around 0.8567 meter. This should be the length of the pipe. Just check we have made any mistake here somewhere. Just check this consistency of this. Other than that, I think everything is all right. Okay. Can we stop here? Unless any more question? Hello.
Yes, sir, you can stop.
Please check the consistency of that part which I have made it in red. Okay.
Okay, it is correct.
Okay. So we stop here and see you on Thursday.
Excuse me, sir.
Yes, please go ahead.
Sir, I had a query regarding quiz I mailed you, so please could you check your mail?
What was the query?
Sir, actually, I think the order of answers was different. I used the correct formula. I got two options right, so I think my formula was right. But
No,
the
I
answer,
think you check your calculation, because there are many students who got out of marks. So there is no question that the answers are incorrect. But I will check again. You
Yes,
please
sir,
check your calculations.
yes, sir, I did check. I even attached a photo, so you can.
So I will check. No problem. I'm waiting today to all the queries to come. So I will check it. And only the legitimate queries will be corrected. If somebody